let's start with a little bit of introduction to KNIME. Basically, with our application, with our products, you can cover the entire data science life cycle. So from taking the data, blending them together from different sources, transforming, train your models. So all the creation part can be done with KNIME Analytics Platform. And then as soon as you want to move your data to production, so let's say you're a company and you want to productionize your data science, then you can move to KNIME Business Hub and do all the deployment of your models, consume, collaborations, etc. there. Today, we will only use KNIME Analytics Platform, so only use our open source platform. And the main characteristic of this platform is that it is based on the visual programming paradigm. We call it low code, no code. What does it mean? It means that the main application is built on visual blocks. So if you don't want to, you don't have to code at all. You can do all the data science operation without a single line of code. But it's also, so that's the no code part, but it's also low code, meaning that if you want, then you can also put yourself into coding and put your data science application also by coding in different programming languages within our applications. KNIME, as I said, can cover many data science operations, and it also has a lot of extensions that enhance the possibilities that you have with our platform. So not only data science, but you can also do not only like basic stuff, but you can also extend our platform with text mining extensions. If you want to do cheminformatics, we have a very cool geospatial analytics extension that has been developed, has been launched like a couple of weeks ago or a month ago, and developed by the Harvard University. All of those extensions are for free and open source, of course. And then besides that, we also have many integrations. As I said, if you want to include your code into the visual programming paradigm. So we have integrations for Java code, R, Python, plus integrations to specific libraries such as Keras, Plotly, etc. And especially we will focus on Keras in a minute. I also want to give you a bit more introduction to KNIME. The basic of KNIME is nodes. As you can see here, this is a node, and this is like a unit of KNIME Analytics Platform. And each node performs a specific task, takes some input, does some magic inside, and then outputs the data from the output ports. As you can imagine, you can combine multiple nodes one after the other and do different operations. And this ensemble of nodes, we call it workflow. For example, in this workflow, we read some data, then model a decision tree, then output the model that we predicted, score to measure the accuracy and do some visualizations, etc. So very simple with just a bunch of nodes. But of course, your fantasy doesn't have to stop there, and you can do workflow as complicated as you want. For example, in this workflow, we read data from different sources. So we read data in KNIME, we can read data locally from a database, from the cloud, from big data also. And then once you have those data into KNIME, you can transform them, analyze, do data mining, do machine learning. Then we have a full set of nodes for visualization. And finally, you can deploy your data science application in the cloud or locally or as a dashboard, etc. Since you can access all those different sources of data, then we have to support many technologies. For example, we have integration to support data, to read data from Amazon S3, from SharePoint, from all the different databases. But also, if you want to stay simple, you can also just read an Excel file or a CSV file. Then for big data, we have Databricks, Spark integration, etc. As I said, we have the integration for the different programming languages, such as R. When specifically, we also have integration for Python and integration for Tensorflow and Keras to do deep learning. So that was it for the little bit of introductory slides. And now I would like to give it to Cory to go on with the presentation about deep learning.
Let me share my screen now. So what I want to do to start is give a little bit of a demo of what KNIME looks like. So this is KNIME Analytics Platform. You can see it here as this desktop application that I have installed, installable on Mac OS, as you can see from my screen right now, as well as Windows and Linux. So you can pretty much put it wherever you want. And this is what it looks like. So on the top left, I've got a file explorer, basically. Down here on the bottom left, I have my node repository, which is where I'm going to go to find all of these functional pieces that I can use to drag and drop and compile these workflows to build my data pipeline, as well as some description stuff on the right side. So what I want to do here is show you what it looks like when we are talking about deep learning in this KNIME Analytics platform. So I'll just grab some CSV data here for a really quick and dirty example. You can see that I've already got numeric input data, so that's what I want for a network. Of course, I probably wouldn't actually use a deep learning model of any kind for the Iris data set, but here we can see that we've got the numeric input, but a categorical target. One thing that we like to do to fix categorical targets to work with deep learning models is do some one-hot encoding. So we can do that with one of these nodes. So don't worry too much about what these are. I just kind of want to show you what the process of working in this looks like for a second here. So here's my target. I want to kind of break that up a little bit here, and I can see that now I've created these new columns that are one-hot encodings of that category, which is what I'll need to use a deep learning model. And if I'm going to do that, I'll probably partition my data too. So I have my training and testing set. In this case, I'm setting it up so that it's 70% split randomly, but you can see there are a few other options for how I do that partitioning here. Now, when it comes to designing a Keras network architecture, which is really the bulk of working with deep learning, is trying to decide what your architecture should be, and then on some of the bigger models, trying to figure out how to actually train all of those parameters, of course. But let's see. So if I want to see what kind of options I have for Keras here, you'll see that there are different nodes that represent the different types of layers available in the Keras package. So you should basically be pretty familiar with this if you've used the Keras package before. There'll be a function for adding a convolutional layer. There'll be a function for adding a dense layer and things like that. But what I'll start with is an input layer. In this particular dummy example, my input is just a single dimensional 4-unit vector. So I'll just say 4. If I was working with images or something, I might say the input shape is 256 by 256. That's one common image shape. And of course, this can be whatever it needs to be. So that's just fully customizable. We'll just say 4 for now. In this case, I'll probably just do a really simple network. So let's just add a pair of dense layers here. I can go into these, configure them just like the input, see how many neurons I want in that layer. Maybe I want to select my activation function, and so on. And then I'll add one more layer here just as my output. In this case, I've got 3 columns that represent which of the categories my classification. When I'm building this multi-class classification model with a network here, I'll often use something like softmax for my output activation function. And then this is how I've defined my network architecture. So there's lots of times I use Python, and there's lots of times I love using Python, but I do find it very simple and straightforward to build my network architectures in a platform like this. Now, if I wanted to add a custom layer, just because I know this is probably the place where that question might come up, there are these editors here. So maybe I want to do a deep learning network editor. Let's say I want to do something like this. I can bring this in, I can connect that, and then I'll have this pre-created architecture, and I can pass it into this Python editor. So I can make some additions. Maybe I want to add a custom layer in there or things like that. But when it comes time to train this, I can use the Keras network. Oops. Here we go. I can type. Right, so when I get done creating my architecture shape and I've prepared my data, I can also configure a lot of these options that are relevant to how my model gets trained on that architecture. So I'll be able to choose which of my data columns represent the inputs to those that input layer. I can select which ones represent the values in my output layer, that target column. And I also get a lot of these other options here, like selecting my backend if we have multiple installed. I can select how many epochs or how many batches I want to create in this training. Random seed stuff. I've got a lot of options for selecting different optimizers, as well as some advanced options like early termination, and some CUDA customization here, some CUDA selection. If we have a NVIDIA graphics card with that supported, we can do that with the Keras GPU package here. And that'll all run here. It'll have its learning monitor that you're familiar with from Keras and all of those kinds of things. So it's really just an easy way to access that Keras functionality in this streamlined environment. Okay, so that was, now that you've seen what KNIME looks like, we've already talked a little bit about networks, but I kind of want to give a review here before we start talking about these different use cases from our agenda. So the term neural network, we've probably all heard it a million times now. It's been around for decades and decades. The term was inspired by biological neural networks like brains, where we have neurons that have inputs, all these different dendrites at the beginning of the neuron cell that accept these different activations from prior neurons. There's a cell body and this axon where these signals pass through and make it to the end or don't. And in that way, there's some processing. And what kind of happens between these inputs and these outputs are what we'll think of when we get to the deep learning part here, the actual artificial part, as the activation functions processing these inputs. We then end up with a network of neurons when we link them back to back. So what that looks like when we start kind of artificializing it, if you will, is we have our different data inputs. In the little demo I gave you, I showed you those that iris data set. So that's a data set that contains information on size and lengths of petals on flowers and stuff like that. So we've got these different numeric values that represents our data points. So those are what we can think of as these different X1, X2 inputs. And then there's an activation function. That activation function could be something super simple, like just adding up those values. These different functions that combine them. Some common ones are linear functions. So that would basically be just adding them up. There's also the ReLU, which I showed you a little bit, which is a regularized one, but we won't talk too much about the different activation functions. It's just a function that does something to those two inputs and gives us a value out. Those activation functions have something called weights, and those are what we train when we train an artificial neural network, is these weights. So some of the famous models in the recent years have many neurons, many layers. So here's an example of an activation function. And as you can imagine, many parameters to optimize. That's really been the game of pushing the envelope with deep learning here, is not just how can we design a better architecture. I mean, that's been a huge deal with stuff like transformers, which we won't be covering today. We'll cover some of the precursors where we can kind of make better use of the networks that we do create, but also how do we train a model that has this many parameters? So the most basic kind of neural network is a simple feed-forward neural network. So in this case, we have our input layer, and we have these activation functions that produce a second layer of values in a new vector. And this repeats as many layers as we have in our model until we get to an output where there would just be one, in this case, activation function producing that single output value. So how do we do that from the KNIME side? So you've seen this graphic here. So KNIME is a open source data science platform that we produce. It's a Java app. It's you can check it out on GitHub and all that stuff, and on our website if you want to see more of it. It's a Java app. It's based on Eclipse, and we have integrations with a lot of tools. A lot of deep learning work is done in Python. Some of these packages are, of course, actually built in C, but a lot of these famous packages like TensorFlow and Keras are Python packages. We kind of start with KNIME's integration with Python. So KNIME has nodes built in Python. We also allow coding in Python internally, and we've kind of gone and abstracted away that Python, and you kind of see that happening in these layers here. The nodes that I showed you in the demo very briefly all were based on Keras functions. So those Keras functions are what we choose to visualize through the KNIME GUI. And of course, those are interacting with TensorFlow in Python underneath. We also offer support for the Java-based TensorFlow. If you go to hub.knime.com, you'll be able to see a lot of our nodes, a lot of our extensions, and these are just some of the examples of the Keras integration nodes. I did that slightly out of order, but now we're going to talk about the LSTM. This is the first of our 3 use cases. Obviously, chatbots have been a huge thing in the news lately, with ChatGPT kind of exploding in popularity over the last few months. And they come in a lot of different styles. Like chatbots have been around for a long time. We've seen them used a lot, kind of like more advanced FAQs maybe, where you can kind of type in a question for a chatbot to try to push you to a FAQ page before letting you talk to a person. So that's a common place where we see kind of more basic chatbots. But we also use this text generation for more creative use cases. Sometimes we'll use it for stuff like generating new names for products, or maybe we want to use it to write new poems, which is what we're going to show you here. But there's a lot of different uses for chatbots or text generation models that aren't full-fledged ChatGPT bots. Here's just, again, a few examples of some of the problems where you might want to tackle them with free text generation. So maybe you want to simulate a writing style. Maybe you want to do translation. Neural translation has become huge in the past years as well, or generating some possible product names for new product lines. What is a language model? So they come in a huge variety of different complexities. Language models are, in brief, models that are trained typically on text corpuses, so lots of text data. They often use as an input either sequences of words representing one-hot encodings from possibly a huge dictionary, or sometimes they'll use individual letters from the Latin alphabet, or sometimes they'll use syllables, so little is a space in between. It's harder to train a model that generates characters at a time, and sometimes there are too many possible outputs when we're talking about words, as of course there are tons and tons of words in the English language, so syllables are sometimes a middle ground. In our use case, we have trained this an LSTM network, individual characters. So we have this text input that represents our language, as well as a text output. And we kind of output a probability distribution over some possible continuities to that input language. Some really simple ones are models like the N-gram. Some really complicated ones are transformer models, huge transformer models that require things like transfer learning and reinforcement learning to fit all of the parameters. But a lot of the more kind of day-to-day applications of language models fall back to what was once upon the time the cutting edge of LSTM networks here. So that's what we're going to talk a little bit about, is this LSTM network middle ground. Before we can use text data to do stuff like language generation in this deep learning, we have to be able to process that data. So often what that means is we bring in data. It's a huge text document. Maybe it's all of the works of Shakespeare as our play example today. But we need to clean it up. Maybe we need to make sure all the letters are lowercase. Maybe we need to remove unusual characters. Maybe we want to remove the punctuation. So KNIME has a text processing extension. If text analytics is your thing, definitely check it out. We're kind of just going to move past that today and talk about the LSTM, though. We will have to clean that up and parse out those characters, though. All right. So what is a LSTM unit? So sometimes we'll say LSTM layer, but really an LSTM is a unit. It is composed internally of multiple layers on its own. So what we can kind of see here is multiple LSTM units next to each other. So just think of this block, this A here, as an LSTM unit. We have some input data that comes in, it gets processed by this unit, and we get an output. We execute that model again, and some of that past information is conveyed to that re-execution. That's what we can kind of see here. We pass new input data into our model, but we get a little bit of temporal information from the previous execution of the model here. So we get information there. Now, what does that mean and how does it work? So inside of the LSTM unit, there's a few logic gates. So our input data comes in, and before I talk about the logic gates, let me mention one other thing here. So internal to this LSTM unit, there's also a memory state. So we've got what is basically a vector here. This vector has values in it, and those values hopefully correspond to something relevant to the current state of our system. That could be something like, is there already a subject in my sentence? Just to abstract that idea a lot here. It's just information that is stored. And if things go as planned, when we train and fit our model, it will train in a way where it stores useful things in this memory state. So let's say we've got a memory state. It's coming in from the prior execution of our network. The first thing that happens is we get an input gate here for the forget gate. So we take that memory state, and depending on what input data was passed into our model, we might wipe some things clear. In the example with language, if we find a period in our sentence, in our input data, if that's the input character right now, then we might erase the memory state. We might even erase it completely, or maybe we'll just erase the subject. That all depends what happens at train time, of course. But we kind of have that ability to remove information from our memory state. Next, we have this input gate here. So the input gate processes this input data and appends new information to our memory state. So we have these kind of additions and multipliers. So we bring this input in, we have a multiplication function here that does a pointwise multiplication of these vectors and possibly wipes some stuff out of my memory state. Then we have the input gate, which can possibly add things to my memory state. And then finally, we have the processing that happens over here, where we have this output gate. And that output gate is going to look at what the current state of my memory is, as well as my input values, and process something that gives me an output that is hopefully context relevant. Before we used LSTMs, there was a lot of use of recurrent neural networks, and recurrent neural networks worked similarly, except there wasn't this whole blur of stuff with these logic gates in the middle. We just passed this output as an input to the next execution of the network. And that was great. We got to see what happened last time we ran the model, and we could still do this processing, but it didn't give us this ability to develop an ongoing memory state that could, in theory, stretch back as far as it needed to. So that's the LSTM in short. When we're talking about using it for this language generation, we have our text. We've done some one-hot encoding here, and we're passing these one at a time into our network here. So you can see we've got this dictionary size here. So this is one-hot encoded. So if I've got 26 characters in the alphabet, then I have my one-hot encoding that comes in here. One of my inputs is a 1. All of the past inputs, all the other inputs are 0. And it uses this LSTM network here to have this temporal context about the previous characters in my language to help generate a output that makes sense. That could mean making sure that the next word or the next letter finishes a word. If I do have a complete word, maybe the next character should be a space, and things like that. So we end up holding on to that context there. So this is what the workflow looks like. I'm not going to bring it up and demo it in the interest of time, but we've got our input layer here. We can just use a simple Keras LSTM layer here. You just drag and drop this node in, and you can set how many neurons should be in it, and what activation functions you want to use for this LSTM layer. So you have a lot of customization here without going into the Keras Python code. In this example, we've also added regularization with a dropout layer here. What that basically does is it kind of goes in and at train time and randomly blacks out some of the neurons in the prior layer here. And this is helpful to prevent overfitting at training time. So I also want to show you a little bit about how some more of these layers are configured. So I think I looked at these a little bit when I pulled up Analytics Platform in the demo, but you can see that in this screenshot over here, this is the Keras dense layer configuration, where I can select the number of units as well as the activation function. And we've got support for dense layers, dropout layers, the LSTM, of course, the convolution that you'll see in the next use case. You can flatten layers, etc. So pretty much everything you'd expect from Keras. Once we have our architecture set up, we go over to the Keras Network Learner, where we can configure things like the optimizer, point our network to the proper input and target data. And we can also set the loss function. So this one's really important, of course. When we're doing something like the classification that I was demoing in the very beginning, where I had 3 different classes, we might do something like some categorical cross-entropy loss functions. If I'm doing a forecasting model, which is what I work on most of the time, I'll use things like mean squared error or mean absolute error, depending on my use case there. But we can also code a custom loss function right here in this configuration dialog. So if you check this little radio button here for custom loss function, you'll have a little bit of a Python dialog box that pops up down here, and you can code in your custom loss function. Sometimes that's nice if you have a really specific loss that you want to use. I've used it more frequently if I wanted to combine two different loss functions. For example, if I couldn't decide between mean squared error and mean absolute error, I can kind of look at a sum of both of them. Not necessarily recommending you do that, but there's different ways you can play around with custom loss functions without actually getting into the nitty-gritty of developing loss functions. So, and then of course there's the optimizers. So here's some of the results that we got from training this LSTM network on. We trained it on some rap music, and we trained it on some Shakespeare data. And this example, this workflow is available in one of our final slides. We'll have a link to some short articles about each of these use cases where you can find more content on them. So here is a totally artificial Shakespeare play over here. And on this side is a totally artificial rap song, which, as you can see, is slightly more vulgar as you'd expect. So moving on to my next use case, I wanted to talk a little bit about neural styling. In this one, we'll touch on convolutional neural networks. Neural styling is the process of kind of combining two images, really. We take a first image that represents our style and a second image that represents the thing that we want to impose that style on. So one thing we've done with this in the past is alter our profile pictures, so that's kind of more of a fun application of neural styling here. If we want to kind of induce appearances of art styles into actual camera photos. And this has monetary value, of course, at some companies here. We can think of things like Snapchat filters, etc., where we really want to kind of impose these styles on an image or video. So we've built a data app, again, totally in the open source KNIME Analytics Platform, where we take a image that represents a photo that we want to style, and we select, in this case, from a selection of possible styles here. For example, here's my boss, Rosaria Salippo, and her being transformed into the Medusa painting. So we'll show you what the result looks like here in a second. But that's the idea here, is that we can kind of do that combination there. Oh, I've put the wrong one here, so I'm sorry about that. But we do also have a image extension, which is available to you. This is a picture of the text processing extension again, so my mistake there. But there is an image analysis extension that you'll be able to find. That image extension was built in cooperation with the University of Wisconsin at Madison. So, right. What is a convolutional layer? So when we're working with image data, the kind of layer that we need to use is a convolutional layer. So this gives us a way of kind of passing over an image and extracting bits of information out of it that we can use in this reduction. So you can kind of get an idea here. This convolution is passing over my image, and it's looking for different shapes down here. And depending on the activation function that ends up being fit, we'll get different bits out here. So one thing we might be able to learn is something like, is there a corner up here? Am I looking at an edge? So these different kind of bits of information that you often hear about deep learning being able to extract from images is done by these convolutions. I think it was a few years ago now, when maybe even more than that, we were all talking about, do you remember that one, Emilio? Well, it was the early 2010s one that Google won, and it kind of kicked off everything all over again. But anyway, and then we can show kind of layer by layer what the expression that we get from these deep learning models are. So through our Keras integration, we support 2D convolutions, 3D convolutions, which could be videos, as well as 1D convolutions, which you might use to try to extract bits of info from something like a time series, where you're trying to understand if there's a upward trend, downward trend, etc. So it just gives us ability to extract information from different dimensions. Now, when we're building a convolutional layer, there's a few important things to configure. Things like the kernel size, the stride, and the dilation rate. So going back to this GIF, because I think it's really helpful, this kernel size here is this 3x3 gray shadow that you see scrolling over this square in the bottom. That's the window that I'm looking at my data in. So my portions of my image. And those correspond to new positions in my output layer. So you can see that I'm using this convolution to reduce the dimensionality by extracting information from these windows. The stride is, of course, how far this kernel moves from iteration to iteration. So I could make it move more than one pixel at a time, for example. And then we'll, of course, need to know something about the activation function. So here again, we can see a little bit more about the stride being how far we move, the window being, or sometimes called the kernel, is the size of that section of pixels that we look at for each activation function. And then another thing we'll often do is pooling. And this is another useful way to reduce the size here. A benefit to using these convolutions instead of just dense layer after dense layer after dense layer, as well as this pooling. We see these in VGG16 and its newer iterations as well, is to reduce the dimensionality of these later layers in our network, which is very helpful for not only reducing the number of parameters, but also condensing information. Just to show you really briefly what this workflow looks like when we run it here. This is our neural styling workflow. So there is a little bit of Python in this workflow, so please do check that out if that's of interest to you, where we kind of do a little bit of manipulation here of the VGG model to steal some info there. And here are the outputs that we're able to do using those convolution layers in that VGG-like model, where we have Rosaria's original profile picture up here, and then it recreated in these various art styles. Okay. If anybody is able to guess the art styles without waiting for the text pop-up, kudos to you. And then for the next use case, I'm going to pass it back to Emilio to talk a little bit about how GANs can be implemented in KNIME.
Thank you, Corey. Now we are at the last use case of today, and my use case is about image generation using GANs. First of all, I want to give you some motivations about why do we need synthetic data in the first place. First of all, of course, it's cool and it's fun. As Corey already shown, like you can create some text, some rap songs, you can create some neurostyling of your boss, as we did already. But some more realistic motivation, for example, could be that sometimes you need some data and those data are just not there, or those data are, for example, too expensive, are too hard to collect, or they're not enough, or, for example, in some cases, they are protected by copyright. And this is an example that we will see today. One solution that we have is to create those data from scratch. So to ask a machine, to ask a model to create those data for us. And one method that we will see in a minute is to use GAN, generative adversarial networks. And specifically in this use case, we will see how to use GANs to create synthetic images, so images from scratch. Generative adversarial networks are a specific family of neural networks, and they are very interesting and very particular because they are made up of two different networks. In every GAN, there is always a generator, and the task of this model is to start from some random noise, some random number, and create a fake image. So this generator model takes some, we will see that it will take like 100 random numbers, and out of them, it will create a picture, which is as realistic as possible. Then we have another model, which is the discriminator. And the task of this model is to categorize those images and basically decide if an image comes from a training dataset, so if it is a real image, or if it comes from the generator, so if it is a fake image. So the discriminator just does a very simple classification, takes an image and says, this is real, this is fake. The good thing that happens inside the generative adversarial network is that those two models play a zero-sum game. It means that during training, they become better and better, the two of them, but in the end, one of the two will become better than the other. So either the discriminator will become better in recognizing images created by the generator, will recognize all the fake images, or the generator will become so good at creating images, then the discriminator will be fooled every time. The fake images will be so realistic that the discriminator cannot tell if they come from the training dataset, so if they are actual images of people, or if they are fake and come from the generator. And we will see in a minute that this training is very interesting because it's very interesting to orchestrate between this training of those two models. More in detail, how is a generator made up of? In our case, so this is just the model architecture that we decided to use. The generator takes a random vector, and in this case, it takes 100 random number. And then using a series of transpose convolution, in this case, which are all those layers here, it kind of upscales those numbers, those values, until we get to 128 by 128 by 3, which is the dimension of our picture. So the output of the generator model is actually what we consider a picture of 3 channels. The other model instead, the discriminator model, takes a picture. So the input of this model is 128 by 128 by 3 numbers, basically. And it scales it down step by step using convolution, in this case, 2D convolutional layers, until we get to a single output. And this single output is the probability of that image being real. And that's why with this probability, the discriminator is able to say, probably this comes from the generator, so it's a fake image, or actually, no, this looks good, so it is a real image. All this complexity, we were able to model it using a KNIME workflow. And this is kind of the workflow that we use to train a GAN model, to train a generator and a discriminator together. Besides the training, of course, there is also some other stuff happening in this workflow. So we read our images, and then we do some image preprocessing because we have to polish them. Then we have to define the network architecture, as Corey described before, so build all the single pieces of the network, all the layers. And finally, we can do the training of the network. So starting from the image processing, what we wanted to do, besides reading the images, was to resize them into the same shape and then normalize their pixel values to a common range of -1, +1. And everything that I just described happens in this part of the workflow. So this bunch of node is able to read the images and then resize and normalize them. And those nodes are very interesting because they come from a KNIME extension, which is the KNIME image processing extension that actually Corey already introduced before. And I want to stress that, so natively KNIME, when you download it the first time, it doesn't have those functionalities, so you don't find those nodes. But if you install this community extensions, which comes from the community, actually a university, and is open source or free, you're able to do all these kind of operations on your images. And in this case, we used it to do image preprocessing for our GANs. Then the other cool thing is the actual training of the GAN. It is actually a little bit tricky to explain this training. I will just go through it very, very quickly. But basically, what we had to do is to kind of feed some real images to the discriminator in order to train it and then update its weight, then feed fake images to the discriminator again in order to train it to recognize fake images, basically. And finally, we have to do a third step to train the generator. And in this case, the generator creates fake images, we pass it to the discriminator, we freeze the discriminator weights, and then with the loss, we update the generator's weight. I wanted to describe this training step because it is more complicated than a usual, let's say, training phase of a model. That's why in this case, we relied on Python code. So again, as I said, we have all the Keras nodes to do the Keras integration using KNIME nodes. But in some cases, if you want, you can also use Python code, like in this case, because to model more corner cases situations like training a GAN application, for example. So in this case, if you've learned some Python, for example, in the talk before, don't worry because you can make good use of it. And yeah, of course, I forgot to use Python code to train deep learning models, as also Corey said. We have a deep learning Keras integration that it's also easy to install in KNIME Analytics Platform. Now let's start with the cool stuff, because we didn't just train those models. That would have been very boring, actually. but we wanted to apply those models to generate actual images. And for that, we created a data app. And the data app in Analytics Platform is just an application that is able to display something, let's say in an interactive view. And in this case, this on the left is the data app with just one button. And every time you click, basically we pass some different random numbers to our generator model, and we are able to see an actual face in there. So the training took quite a bit of time, but the images are very small. But they were quite a surprise actually once we saw the results, because they're not that bad, let's say. But actually, after we created this data app, we had kind of an intuition, because what we realized is that we just created those 100 random numbers, fed it to the model, and then something came up. But the intuition is that if we slightly change those numbers that we pass to the model, then we get a slightly different image, like the one that you see there. So we start from this, then we slightly change it, and we get an image that is more and more changing towards something else. So for that, we had the idea for a further data app, which is the image-to-image interpolation data app. Basically, we start from two vectors, and then we create all the vectors in between those two. We feed it to the generator model, and we are able to switch from one face to the other, like you can see there. So they are faces, they are creatures. Sometimes they're pretty spooky, but it's quite an interesting result. And then, of course, it was not enough to just play with faces, but we became very creative and started creating cats, dogs, other animals like lions. But my favorite one, the one that I'm the proudest of, are Simpsons. It was the funniest one actually to train and to see, because in this case the training dataset was a bit small, and that's why I didn't really get the Simpson shape, but it's still funny to see the results sometimes. That was actually the end. Thank you very much for your attention.